In this work, we propose a collision detection framework based on the closed-form context space parameterization, and the geometric models we are focusing on are the convex bodies with smooth bounding surfaces. Collision detection is one of the essential building blocks in the field of computer graphics and robotics. For example, in the motion planning algorithms, one of the most important aspects to be considered is the collision constraint. The small video in the left shows the planning results solved by a sampling-based algorithm, where a majority amount of computational time is spent on querying the collision status for the robot and the environment it's operating on. Another example is shown on the right, where a physics engine is simulating a dropping action. The context status and the context normal have to be queried efficiently in order to facilitate real-time performance. The collision detection problems can be divided into static and continuous cases, and this work considers both. For the static case, the poses of the two objects are fixed. At first, we need to know the collision status. When they are separated, the separation distance is further computed, and the closest points on the surface of the two objects are obtained. When they are in collision, we then compute the penetration depth and the corresponding surface points within the contact region that are furthest to each other. In the continuous case, where both objects are moving and probably deforming, we need to know whether they will be in contact during the whole motion. If they will not collide, we further compute the minimum distance along the whole trajectory. If they will collide, the first time of contact and the corresponding contact point and normal are computed. The geometric models we're interested in this work are convex bodies with smooth boundary. We're using three representative models, ellipsoids, superquadrics, and polyellipsoids, as examples for illustration purposes. Algebraically, we can characterize the surface of an object by its implicit and parametric expressions, and the gradient vector m at each surface point can be computed by taking the derivative of the implicit expression with respect to the surface point. And we're also interested in a new gradient parameterization, which is the inverse function of the gradient expression. And the strict convexity guarantees the one-to-one mapping between the surface point and its gradient vector, so that the gradient parameterization is well defined. By using the gradient parameterization, we are now ready to derive the closed form expression for the context space between two objects. In canonical form, where the two objects are fixed at identity poles, we can establish the contact condition. That is, the gradient vectors at the contact points are anti-parallel to each other. Then we are able to write down the closed form expression of the context space, sigma, in parametric form, which is the shaded blue surface shown in the right figure. Now, if we apply linear deformations to the objects, such as rotation, shearing, and scaling, it is also possible to write the closed form expression after the transformation. With the context space parameterization, we now propose methods to solve the collision detection problems in both static and continuous cases. For the static case, we seek to find the closest point at the context space with the center of the second object. This is formulated as a nonlinear optimization problem, which can be solved by the three proposed methods. For the first one, we directly compute the distance between the center of the second object, which now is shrunk into a point, and the parametric context space surface. The second method applies the common normal concept. The idea is that the vector connecting the center of the second object and the closest point at the context space is anti-parallel with the normal vector at the closest point. So we propose the objective function as the cross product of these two vectors, whose minimum value is expected to be 0. The third method also uses the common normal concept, but applies a fixed point iteration method. The idea is to iteratively update the gradient vector based on the previous two gradients. For the continuous case, we further add another variable of time that parameterizes the motions of the two objects. The objective function is similar to the first method in the static case, which is based on the distance. At each iteration, the closed form expression and the linear deformation is used to update the context space. To evaluate the proposed framework, we conduct benchmark experiments with some existing algorithms which also consider the convex bodies with smooth boundaries. The proposed methods in the static case could run in microseconds for each query, and they are all competitive with the existing methods that we are comparing to. For more detailed statistics on other metrics like accuracy and number of iterations can be referred in the paper. For the application, we integrate the methods in the static case into a sampling-based motion planner, RTConnect, which is sourced from the Open Motion Planning library. The robot links are enclosed by superquadrics computed from the convex hull of the mesh model, and the planning scenes are static and filled by superquadric objects. For the physical experiments, the obstacles are reconstructed by the fitted superquadrics from the point cloud data acquired by the depth camera. The implementations of this work are publicly available. For more details, please refer to our paper and the following links. Thank you for watching.